All right, so in this video we're going to talk about slope fields, and you don't necessarily need to have graph paper to take these notes, but it does make your life a little bit easier. So slope fields. All right, slope fields are line segments that give the slope, not the, aka the derivative. So line segments that give the slope or the derivative at specific points. Each line segment has the same slope as the solution curve through that point. I know that doesn't make a lot of sense right now, but after we see pictures of slope fields and start working with them, then we can go back to that definition and it will make more sense. All right, so this represents the general shape of all solutions to a differential equation. And one thing to specify is that when we look at slope fields, when we see all the solutions, this is going to be a graphical approach. Since an analytical approach is very difficult or impossible. All right, so what we're going to say here is that for our notation, we'll have y prime equals f of x, y. So x value, y value. Okay? All right, so these are best understood when you go through some examples. So that's what we're going to do. And then after we've done the examples, or especially in class tomorrow, if we need to come back and revisit some of this and what it means, we can certainly do that. So we are going to sketch the slope field for y prime equals x minus y for the point negative 1, 1, 0, 1, and 1, 1. All right, so what we do typically is we make a table. So we're going to say we'll have 3 columns to our table. We're going to have the given x value and y value, so negative 1, 1, 0, 1, positive 1, 1. And then we have y prime, or the slope, at that specific point. So this slope is also known as the derivative. So if we plug these numbers in, negative 1 minus 1 is negative 2. 0 minus 1 is negative 1. And 1 minus 1 is 0. So what we do now, here's my x and my y axis. Now we go ahead and we draw those slopes. So at the point negative 1, 1, so left 1, up 1, we have a slope of negative 2. So negative slant, pretty steep. At the point 0, 1, we have a slope of negative 1. And then at the point 1, 1, we have a slope of 0. And so that's what part of our slope field would look like. All right, so what we're going to do next is we're going to work with the little sheet that I gave you where we're going to match the slope field with its differential equation. And hopefully you guys can see these kind of okay. They did not photocopy as well as I'd hoped they would. Okay, so if we're going to go ahead and work our way through each of these, and as you guys can see, there's a lot of points here. So we have, it looks like every half at x is 1/2 and y is 1/2, they have a value there. At x is 2 and y is 1/2, they have a value. They have lots and lots of these little slopes. I was pointing to a part where you couldn't see. They have lots and lots of these little curved these little lines here. So what I'm going to go ahead and do is I'm going to start with the first one. So that was just I. And I'm going to think through what some of these slopes should be, and then we'll see if we can match it up with one of the slope fields. All right, so what I typically do is I look for what's happening at the axes. So when I see that the x value is 0, then the slope should match whatever the y value is. So if I have the point 0,1, my slope would be 1. If I have the point 0,2, my slope would be 2. If I have the point 0,3, my slope would be 3. If I have the y coordinate is 0, the same thing would happen. So if my x value is 1, my slope is 1. If my x value is 2 and my y value is 0, my slope is 2. And so that's what I look for when I look at these slope fields, as I'm saying, okay, when the x value is 0, so that's the y-axis, when the x value is 0, then all these slopes along the y-axis should be different. So number 1 should be kind of slanted, number 2 should be even more slanted. So that definitely does not match with A. But if you look at B, you can see that it does that. Here's a y value of 1, y value of half, y value of 1, y value of 1.5, y value of 2. That makes sense that our slopes are increasing like that. Here, our slopes are decreasing. So I can definitely see that happening. If I need to double check, I can look over here and I can see the slopes are kind of doing the same thing over here, and so I know that it's going to be between B and C. I'm just not sure which one yet. Okay, so can you guys see how that's doing kind of the same thing that we expected? All right, so now I'm going to go ahead and I'm going to look at the other points that I had, which was where the y coordinate is 0. So if I look at B, when my y coordinate is 0, then these positive x values are giving positive slopes that are increasing in steepness, which is what I would expect. Same thing on this side. So B is still a good candidate for the first one. If I look over here, to me it looks like all these slopes are actually 0. Like I don't know if you can tell, but I can see like horizontal dashed lines there. So B matches up with I. All right, let's go ahead and let's look at double I. So for double I, we have y prime equals x. And I love these problems where they only have one variable because they're a lot easier to see. So if there's only an x value for your slope, that means that your slope matches your x value. It doesn't matter what the y coordinate is, that's always going to be the same. So when x is 0, you have a slope of 0. When x is 1, you have a slope of 1. When x is 2, you have a slope of 2. So that means that when you look at your slope field, you're going to have these vertical lines where the slopes are all the same. And you can see that that's this picture right here. So here's where x equals 0, so we have a horizontal slope there. Here's where x equals 1. And so we have all these slanted slopes. Here's where x equals 2, and the slopes are more steep. On the other side, we have x equals -1. There's our slopes there. And then x equals -2. And so A definitely goes with double I. And then I didn't even write anything. So I'm going to say if x is 1, 1, 1, y could be 0, 1, or 2. It doesn't matter. The slope is still 1. If x is 0, 1, 2, 3, it doesn't matter what the y is. The slope was still 0. Okay? So that's a nice trick. Anytime you're looking to find a slope field where you only have one variable, it kind of helps to know that, okay? So I'm going to write a note to myself here. Y doesn't matter. All vertical lines have same slope. Or maybe instead of saying lines, you should say columns. Maybe all vertical columns. It's probably better than lines. Okay. And then last one we know that it's going to be C, but now we can go ahead and look at Y. So what I like about this one, again, is it only has one variable, so that means that no matter what the x is, the only thing that tells us the slope is the y coordinate. So here, instead of seeing those vertical columns that are the same, we're going to see horizontal rows where it's the same. So here, this is where y is 1/2, and so all of these have a slope of 1/2. Here's y is -1/2, so we have a slope of -1/2. This, like I said that I could kind of see it before, this is y equals 0, so we have a slope of 0 here. Here we've got y equals 2, so we have a slope of 2. So that one is triple I, and the reason that it's triple I is because we do have all of those rows being the same. Okay, so I'm going to write that down for this one. X doesn't matter. All horizontal rows have the same slope. Okay, so we're going to go ahead and do one more example. There we go. All right, example. We are going to sketch the slope field. For y prime equals 2x plus y, and then we're going to use the slope field to sketch the solution that passes through one, 1. All right, so first we're going to make our slope field. So I'm going to have my x values and my y values and my slopes. And what I'm going to go ahead and do is I'm going to say that's 1, 1, 2, -1, -2. Okay, so sometimes people do these different ways. I've found that I like to start with my axes, and so what I'm going to do first is I'm just going to say that my x value is 0 and my y value is 0, 0, -1, 0, -2, 0, +1, 0, +2. So if I do 2x plus y, then I get 0 plus 0, 0 plus -1, 0 plus -2, 0 plus +1, 0 plus +2. So at 0, 0, we have a slope of 0. At 0, negative 1, we have a slope of negative 1. At 0, negative 2, we have a slope of negative 2. 0, positive 1, we have a slope of 1. And then we have a slope of 2. Okay. For my y-axis, I'm going to say 0, positive 1, 0, positive 2, 0, negative 1, 0, negative 2. And so we have 2 plus 0, 4 plus 0, negative 2 plus 0, negative 4 plus 0. So at 1, that was 2. At 2, that's 4. That's pretty steep. At 1, that's negative 2. At 2, that's negative 4. Okay. And then we have to fill in all of these. So I've got 1, 1, which is 2 plus 1, and that's 3. So 2 plus 1 is, 2 plus 1 is 3. And then I've got 1 and 2. That's 2 plus 2 is 4. 2, 1, that's 4 plus 1 is 5. And then 2, 2 is 4 plus 2 is 6. All right. So as you can see, it's pretty tedious to draw a whole slope field. All right, we've got negative 1 and 1. That's negative 2 plus 1 is negative 1. Negative 1 and 2 is negative 2 plus 2 is 0. I don't know why I wrote that equal sign. Negative 2 and 2 is negative 4 plus 2 is negative 2. Negative 2 plus 1, positive 1, is negative 4 plus 1 is negative 3. Okay, I'm not going to do all the ones on the bottom, but I'll at least do the ones. All right, negative 1, left 1 down. So that's negative 2 plus negative 1 is negative 3. Negative 2, negative 1 is negative 4 plus negative 1 is negative 5. And then we have 1, negative 1, which is 2 plus negative 1. And 2, negative 1 is 4 plus negative 1, which is 3. Okay, so if we want to sketch the solution through the point 1, 1, the point 1, 1 is right here. And so what we do is we say that if we could have lots of other little slopes in here. And what it means is if you follow, kind of let your line follow these slopes so that your line has the slope that's represented as you get closer to these. You can see how my slopes are kind of getting less steep, hitting 0, and then getting steeper again. then the actual curve that had the point 1, 1 would have looked something like this. The curve that had the point 2, 0 would have been down here more. All right, so this is that idea of when we integrate something, we have that plus c on the end, and that's a constant that's a vertical shift. It moves your picture up and down. So this is allowing you to have all these different curves with different plus c values on the end. So this one was probably 0 or very close to 0. But if we were to use this point as one of the points on the curve, then our value would have been something right in here. So it still would have had that parabolic shape, but the bottom of it would have looked a little bit over here, and it would have come up through the y-axis. So we can find lots of different approximations based on this graphical approach, and that is something that you could possibly end up doing on the final. So if we go back and we consider like that original definition, we would call this the solution curve, and this is the solution curve that's going through that point, right? And so these are little instantaneous rates of change on all these different points that are solutions for that differential equation. And we don't have our solution curve very populated. Like you can see that these examples we had here had a lot more of the little slopes in there. The better your picture is here, the easier it is for you to be able to follow a specific solution. So on this one, if we wanted to follow the solution for 1, 1, here's 1, 1 right here, we could follow this one fairly easily. And that's because we have so many more slopes in there, it makes it much easier to do. So anytime you're sketching a slope field for a specific point, you want to find all the slopes right around that point and then do enough of them so that you could follow it fairly easily.